Any questions? Let's talk more thermodynamics. Woo! Oh, and I forgot I have stuff to hand back. All right, the stuff that's written mostly in purple over on the left-hand side, it's not any information that you have to have memorized, it's just information that will be nice to know. In terms of subscripts here, this is H2O, and in parentheses I have an L for liquid water. So H2O being water, liquid phase. H2O solid, that's for solid, so this is ice. And then gas, this is steam. That's an AL and that's an FE, AL for aluminum and FE for iron. So we talked yesterday about specific heat, I believe. And so we'll just start out with last Tuesday. So I'll just start out with, I got a bunch of boiling water and I'm taking an aluminum cube and I stick it in there. Now the reason I do that is I didn't tell you how much boiling water there is, excuse me. But I want to get the aluminum up to some high temperature, because then I'm going to take the aluminum cube and I'm going to stick it into the water that's at 20 degrees Celsius. Now to do that, the aluminum would need to be in the water for, let's say, 5 minutes in order to get up to the temperature of boiling water. Which to me raises the question of what's the temperature of boiling water?
120 something? No?
Not in any conventional unit system.
Oh, okay.
All right, what's the freezing point of water?
32 degrees Fahrenheit.
All right, so if we're on the Fahrenheit scale, so water. God, I did this yesterday. All right, suppose if I just did that. Nope. All right, what I had to do yesterday was reboot it. Good thing I didn't write all that stuff on this.
Where are those in the textbook?
There's numbers.
Yeah.
There is a table, yes and no. I'm pretty sure this one is, Hewitt sticks to the standard, international standards, and so he has aluminum at 2,700 kilograms per cubic meter. Yeah, that's not wrong. Typically, densities in everyday life, you typically use grams per cubic centimeter.
Okay.
All right, take two.
212 degrees Fahrenheit.
What's that?
212 degrees Fahrenheit?
There we go. All right.
Okay.
So water. So freezing. And then boiling. So this would be 32 degrees Fahrenheit or 212 degrees Fahrenheit. What about in the Celsius system?
Is it 0 and 100?
So 0 degrees Celsius, 100 degrees Celsius. Now, obviously, Fahrenheit is what we're used to, or I assume all of us are used to it. However, that's science, so let's do degrees Celsius. So the boiling point is 100 degrees Celsius. What happens when water gets to 100 degrees Celsius?
The molecules are being affected by the heat.
Well, they're being affected by the heat before then, too.
Mm-hmm. They're really turning into steam?
Right, and the steam does what?
Evaporate?
I'm not gonna nitpick that,
Turn into gas?
it does turn into a gas, either way. Now, there is a difference between boiling and evaporating. Boiling is when you turn it into a liquid to gas using heat. So you put energy into it. Evaporation happens just when a molecule happens to reach the right speed and escape.
What is that symbol on the bottom two equations? It's like a fancy P? Is it a P?
But this,
Yeah,
those are rows,
rows.
3-letter row,
Okay.
and it's the symbol for density. So the density of aluminum is 2.7 grams per cubic centimeter, and for water, 1 gram per cubic centimeter. All right, so we get, so it basically turns, we get the energy gets put into the molecules, it does become gaseous at that point, and because it's a gas, it is less dense than the liquid, it will rise and escape. So that's why the liquid water should not get above 100 degrees Celsius-ish. Now, it is possible to boil water or to take water above 100 degrees Celsius and keep it in liquid form. How would you do that?
Put a top on it.
Pretty much, pressure cooker. And it's also possible to get it to boil at less than 100 degrees Celsius. You can boil water at room temperature. How would you do that?
Put it, no, I don't
Put a top on it.
Put a top on it, is that what you said?
Cause I mean, everything's just in there.
No, putting a top on it probably would not do it. Yeah, you need to somehow drop the pressure. That you've got this pressure pushing down on the liquid, and if you get it above the boiling point, but it doesn't boil, that's called superheated liquid or pressurized liquid. I don't know if any of you experienced putting water in a microwave and you pull it out and then you put something in the water and suddenly it goes boom. Okay, at least one person. That's a superheated liquid, and so all it takes is just the tiniest disturbance to get to actually boil. But we're talking just normal, I have it sitting on the counter, boiling water. It's gonna be around 100 degrees Celsius, maybe a little bit less, but roughly that. Well, lower temperatures, you drop the pressure, so you either put it in a machine which takes pressure out, or take it high up. Water in the mountains does not boil as high a temperature as down here. All right, so we now have this aluminum block at 100 degrees Celsius. So my initial temperature of the aluminum is 100 degrees Celsius. I'm going to take that aluminum block, and through the magic of the board problem, I'm going to transfer that still at 100 degrees Celsius and stick it in this water here. Now, I've got this extra insulation here because I'm trying to apply, this is going to go into here. And then we're going to cap it so that no heat escapes. Now, through the magic of the board, I'm transferring it and maintaining its temperature until it gets in the cold water. In reality, when you do the lab, you just have to transfer it very quickly. So now I've got this block of metal at 100 degrees Celsius. I stick it in the water at 20 degrees Celsius. What should happen in general? Not looking for specific numbers, but what should happen to the water? What should happen to the aluminum?
Water temperature increases and aluminum decreases.
Yeah, it will eventually, assuming there's no energy loss, reach an equilibrium temperature. And that is what we're going to try to figure out. What is the temperature, the final temperature of the water in the block? so in order to do that, we will need to figure out what the mass of the aluminum is. I gave you the dimensions. It's approximately 27 cubic centimeters, but let's see if we can get more precise than that. If someone would be kind enough, this is length, width, and height. If someone would be kind enough to tell me the volume of the aluminum block.
$27.18.
27.18.
Yes, is that?
Anyone else get the same thing? Okay, got a couple nods. What would the units be?
For volume? Centimeters square, cubed,
How many centimeters did you multiply?
3, so cubed.
Cubed. 23 cubic, or 27.18 cubic centimeters. That is the same thing as 27.18 cc's. Cc's really should not be used in science in here, but in case, I hear cc's on TV, so it's just cubic centimeter, which is also the same thing as 27.18 milliliters. All right, so I know the volume. I need to figure out what the mass is. Well, that's why that's why I did the density here. The density of aluminum, as was discussed last time, tells us how much, basically, it's a measurement of the amount of mass in how much space. The density of aluminum is 2.7 grams per cubic centimeter. Grams is a unit of what? It is not weight,
Yeah.
it's the other one.
Mass.
Yeah. And cubic centimeters, unit of,
Length, measurement, or cubic centimeters, volume.
volume, yes. So our density of the aluminum, density in general is mass divided by volume. This is what the ratio should be for aluminum, give or take. And that's gonna be equal to the mass of the aluminum divided by the volume of what we have, which is 27.18 cubic centimeters. So the math problem is 2.7 over 1 is equal to m over 27.18. That's the math problem. And solving that math problem, what is the mass of our aluminum block?
$73.39. Grams.
Anyone else get the same thing? All right, good. One person at your back.
Yay.
All right, questions up to here before we, so this is all calculations dealing with stuff before it actually goes into the water. The mass isn't gonna change of the aluminum, presumably, unless it melts as you're moving it. You'd be in trouble then. Questions? All right, so now I have this aluminum block that's gonna be giving off energy. I have the water that's gonna be gaining energy. I have it in an insulated container in the lab, a styrofoam cup. And I want to figure out what the final temperature is. I know, I'm losing no energy to the environment. Nothing's going out, all of it's staying within here. All the energy stays in here, then whatever the aluminum loses, the water has to gain. I know my total change in energy has to be 0. Which means the change in the energy of the aluminum plus the change in energy of the water is 0. Those are the only two things that I got my perfect container over there. Nothing passes the barrier. We're talking now about this change in energy because of temperature differences. We have a different word for that. That was introduced last Tuesday. So what is the word for energy that is transferred because of temperature difference?
Thermodynamics.
That's the general
Okay,
broad category.
gotcha.
Thermodynamics would be the study of that and other things. I guess somewhat of a hint. We're talking about the quantity of energy transferred.
Thermal energy?
Pardon?
Thermal energy?
No. That's a generic catch-all phrase. Quantity, Q.
Is it Kelvin?
Say it again?
Kelvin?
That would be a unit system, looking for a quantity.
Heat? Heat?
That's the heat.
No, right here.
Heat's the quantity of energy that gets transferred because of temperature differences. So this is basically Q of aluminum plus Q of the water is equal to 0. And Q stands for heat. It would have been nice if they had used H or something like that, but H is actually reserved for something called enthalpy or enthalpy, depending upon who taught you to speak the word.
So they're the same thing?
Pardon?
The change in energy plus the change in the H2O are the same thing as Q?
Yes, this is just generically, there's going to be an energy changing, and specifically because it's a thermodynamics chapter, we're calling it heat. But we're in luck because we have a formula for the heat transfer. And what is the formula for Q? Assuming no change in phase, and I hope the water is not boiling, and I hope that the aluminum block is not going to melt.
Is it MC? Change the D?
Faded off there at the end.
MC
Delta.
delta T?
Yep. MC delta T. I know the mass of the aluminum. I know this C, the specific heat of the aluminum. That's the stuff written in purple over there. Change in temperature, that's what I'm trying to find out. So I take the mass, well, I'll just stick it. So I got the mass of the aluminum times the specific heat of the aluminum times the change in temperature of the aluminum. And that's going to be equal to, I'm just going to go ahead and bring Q over, the negative mass of the water times specific heat of the water times the change in temperature of the water. And there's a negative sign there. Let's stick some numbers in. Mass of the aluminum, we figured that out already. That was 73.39 grams, so 73.39 grams. specific heat of aluminum. Oh, there we go. I have it here in terms of joules per gram degrees Celsius, and here in terms of calories per gram degrees Celsius. Which one do you want to do?
Joules.
I heard joules. All right, so 0.9. 0.9 joules per gram degrees Celsius times the change in temperature. Change. If I'm doing change in temperature, what am I subtracting from what?
The original from the other. Did you take the 100 minus the 20?
No.
No. Okay.
Change. Whenever you're finding change, what do you, it's what minus what?
Initial minus final. Or final minus initial.
There we go.
So 20 minus 100. Okay.
So it's the final temperature of the aluminum minus, minus the initial temperature of the aluminum equals negative mass of the water, and I told you it's 100 grams. Specific heat of water, 1. Oh wait, no, we're doing joules, so not 1. 4.148 joules per gram degrees Celsius. Times change in temperature of the water, which is the final temperature of the water, minus the initial temperature of the water. Got that crammed in there. Let's see if we can. I'm gonna rewrite this on the next page. So I have 73.39, the mass. Specific heat was 0.9 times T final of the aluminum minus 100